All right. I keep sliding further and further. So I have like one more week of attractor point stuff to work through. It's a little bit of everything with attractor point, but we're going to say looking at how to manipulate surfaces and subdivide surfaces parametrically. And we're going to go about that by using crossover. Things like a curve interpolated out of a point and use surface on a grid formation. So first thing we're going to do is just build a curve from what's called a graph mapper. I'm going to open Grasshopper before I do anything else. All right, so we're going to use a graph mapper, which is this funny looking block. And we're going to use output set to create a series of points that we will then use to define a curve. So if you right click on the graph mapper, once you have it open, you have a set of graph type options. You can choose any one of these. We will use a parabolic graph for now. And once you select that, it's not giving you any data yet, but it's going to transform the set of data that you put into it. So what we are going to do is create a range for this graph. So I'm just going to construct a range, and I'm going to use a number slider. And this slider is, in the end, going to determine how many points we have. I'm just going to set it to integers, and I'm going to make the maximum 20 or so. So we have our number of steps. I'm going to let it default to 0 and 1. And I am just going to throw this guy into the graph mapper. And see, it's not doing anything because my number slider is set to 0. 13 or so. And now with that range between 0 and 1, you can see that the graph mapper has output a set of points located on a parabola. Right? So the maximum on the range 0 to 1 on either end, and it drops down, approaches 0, and then comes back up like you would expect from a parabola. So we have that set of points. We have our base set of points. So we can now use that, or use those values because they're not points yet, really, to create or construct a point. So the construct point command we've used before, but it's going to ask us for an x, y, and a z input. If we're just working in 2 dimensions, then we can leave the z as 0 because in the xy plane, our z-axis. So what I'm going to do is manipulate the set of points so that it's more dramatic than just X and Y. Because if we do that, tiny, first of all, we do have something going on though. So what I'm going to do, put my panel down so it's not taking up my entire screen. I'm going to use a multiplication command. And I'm just going to increase the intensity. I'm going to just copy the slider over, actually. Settings I want already. And make sure that works its way up there somewhere. I don't know who else walked in. I'm going to multiply our values by 15 so that we can increase the intensity of the curve. So that's one set, and if we copy it down, I'm going to, for the second one, take the values straight out of the range instead of the values out of the graph mapper. So if we look at this in a panel, our 0 to 1 becomes 0 to 15, right? And our mapped components become across the same domain or range in this case, amplified by a factor of 15. Have I lost anyone yet? Just into the range values, because the range is always going to output a set of values. It's just taking our base domain, which we let default to 0 to 1, and dividing it into 13 steps. You know, if we change our 13, we're going to change the number of steps. And those numbers of steps are visualized by the red vertical lines in the graph mapper. Those are the points that it's being divided at. All right, so now that we've got that, we can come back over here to our point command. And I'm going to take this bottom function, so our values based off of the original domain, be the x coordinates. And see, now we've got a row of points doing something over here. And then I'm going to use the graph mapped component or graph map values as our y values. So I took the bottom piece and I took the top piece, or the bottom piece into the x component of the point and the top piece into the y component. If you switch them, you get a parabola as well. It's just turned to the opposite direction. I'm going to leave them where we expect a parabola to be found. And then I'm going to use an interpolate curve command, or interpolate data. And it is, I'm going to find the curve. There we go. You might have to type it all the way out. If not, it is under curves, lines, top. So I'm going to, the interpolate curve is going to ask for a set of vertices, so points on the curve that you want to create, a degree of the curve, which in this case it is a quadratic of degree 3. We're just going to leave that one be. Typically, we can leave that one alone. The periodic curve, then we do that. And the knot style is uniform because we're not doing range. So it is under the curve tab in the subset. And if you type out interpolate curve, it'll come up. There are like 5. From the one that I pulled up first was a linear one, which won't work for the curve that we want. I'm just going to plug our points into the vertices, and it is going to interpolate a smooth curve from those points. It does not just connect the dots. It's taking the point location and extrapolating a set of data to match a smooth curve. So we have used a graph mapper component to create a series of points. We multiplied those points based on a constant so that we got something more than just a little tiny thing at the very corner of our origin plane. And then we have used the interpolate curve component to create a smooth line running the point. And that is really a best fit line if you're familiar with statistics. But we can come over to the graph mapper command, and the graph mapper has these drag points, and you can edit those drag points. And the graph will lock to a parabola, but you can change the intensity of the parabola. Or if we right click, go back down to graph types, and say let's fit a different kind of curve. Start to play with the different curve types Graph Mapper provides. You can see it's going to continue to give us the point. It's going to continue to extrapolate that curve as long as we have a valid set of values. If you want it to be a sine curve. That. Lines get kind of funny. That's okay. So, questions about that? Cool. This will come back in a little bit. So the next thing, getting a surface with a bulge based on attractive point. So what I'm going to do is I'm going to swap back over to my perspective view in Rhino. I am going to draw a vertical plane in Rhino. I'm not going to deal with creating it in Grasshopper. Drop it into shaded. So this is the surface that we're going to work on deforming. And I am going to just bring that into Grasshopper using a surface data point. That one surface. And life is good. Have our surface Grasshopper. Well, let me know when you all get that far. I don't want to leave behind here. Do it with a vertical or a horizontal surface, it won't make a difference in the end. The assignment that we're going to work on asks you to do it in a vertical surface, but it's as simple as changing the orientation of your plane, whether you drew it vertically or in, So we've got our surface in Grasshopper. And the first thing that we're going to do is subdivide it. So we've done this before, but I'm going to here. I want. I'm going to find it like this. I'm going to go into surfaces and utility. It's divide surface, not subdivide surface. Now, if we here, we'll probably see it under divide surface. Yep. Technicalities. But there's that little bit of information. And I'm going to drop a set of sliders in. Again, I'm going to set them to be, maybe 0 to 50. But I'm going to lock them to the integer numbers so that we don't have weird fractional stuff getting in the way. So we have our surface that we want to subdivide. So I'm going to drop it into this S, which is asking for the surface to divide. And then the U and the V are locally defined X and Y values. So the U and the V is a coordinate system based on the surface that you're working on. So I'm going to just bring this guy up to 23. And I'm going to use that to define my U and my V. I have effectively a bunch of little rectangles, or the vertices for a bunch of rectangles. All I have right now are points. The next thing I'm going to do, now that we've divided these points, is I'm going to define an attractor point. We're going to use to offset and shift and to pull at this surface. So just like we always do, I'm going to drop a point in Rhino and move it somewhere close to my surface. I hid my surface or my plane in Rhino, and I'm going to bring it back so I can snap to something. Now that that's out of the way again, I'm going to bring it in as a point grasshopper. Now, just like with any other attractor point, the closer it is to the surface, the more dramatic it'll be depending on how you set it up, but you can always move it around after we've set up the grasshopper script. Set that as my point. And I'm going to use these points that we found from our subdivision as my reference points for our distance between points for our control point. So if our control point is the B and our set of points are the A, we have panel and we can see we've got all of these different distance sets based on how they're set up. Yes. So this is a list. It's grafted. If we flatten it here, it'll turn back to a solid line. We're going to want this to be flattened later. So we'll flatten it there. And that then means, see, now we don't have any sublists here. We have a one-dimensional data set that's just all of our elements in a. So given that distance set, we're going to use another graph mapper to define the shape form of the bulge that we're going to pull out. I'm just going to drop the wrong graph. I'm going to drop a graph mapper in, and I'm going to set the graph type as a conic for now. Sorry. Parabolic, and I'm just going to invert the parabola. Up a little bit. If you double click on the graph editor, it will bring up a different set of options, and it'll show you your X, your Y bounds on the graph. It'll show you the description and the class name of the graph. So we have a parabolic distribution, we have an actual parabola, and it'll show you whether or not the graph is valid. And for what we're doing, leave the y values at 0 to 1, but what we're going to do is change the x value maximum or endpoint 40. So you can see that our little range and domain numbers shifted. And good. Up seeing a set of bounding lines up with our axis. I do not have any. If not, no worries. So we're going to do the same thing above us, but instead of creating a set of points, we're going to use range as our domain for a remap like we do with attractor point. So I'm going to drop our distances into the graph mapper. I'm going to find the bounds of the data set graph mapper is outputting. And I'm just going to use a panel to visualize that. So a little bit small. That's okay. Play with that and see the bounds are going to change as you graph. So I'm going to drop a remap command in. And just like we've done before with command point or control points, we have our source domain, and that's going to be our set of bounds. We have our original values, which are going to be this output from the graph mapper, which we can again start to visualize with the panel. And we're going to construct a target domain. So I'm just going to construct a domain. And I'm going to use a set of sliders. I'm going to come back over here and just copy one of these guys over. I'm just going to use a set of sliders to construct a domain somewhere from 0 to 50. And that domain is going to be our target domain that we're going to remap all of our values. So when we remap our values, see we get a source domain. That happens. So once you're there, we're going to use an amplitude. And remember, the amplitude is the length or the magnitude of a vector. So we're going to set the magnitude of a set of vectors. If we come back over here, remember we used the subdivide command. One of the outputs is the normal vectors of the surfaces at the point. So if we in here and look at vector display and plug our vectors into the vector display, our point sets, you can see that it's generated this set of vectors, unit vectors, so they're all a magnitude of 1 right now, based at every point and perpendicular to the surface. So if we take these normal vectors, plug them into our amplitude, and then remap, use our remap points or values as the new amplitude. And then if we bring our vector preview over and turn our vectors back on, some really massive vectors. If we can't solve that a little bit, because that's a little bit much to work with. So you can see as we shift the parabola. How did I preview the vectors? So instead of plugging the base one, the original set of normal vectors in, I just took the vectors out of our amplitude. So what I've done is we remapped everything, and then we created an amplitude based on the original vectors and the remapped values. And then we used a visualize vectors or vector display with the vector output from the amplitude and the points on the surface as the anchors. So what I did is I just changed the domain size to bring it back down so it's a little bit more. Right. So we're going to start to move our base points now based on these attractor point vectors. So I'm going to drop a move command in, and we're going to come back all the way to the beginning, and I'm going to grab these points off of our subdivide surface, and those are going to be the elements that we move. And then our vector amplitude is going to be our transformation vector. Right. going to come over. So we should be getting the opposite of what's going on right here, which is that there is a extrusion off of the surface instead of the entire surface being, or instead of the entire surface being pulled away like that. So quick troubleshooting. Opposite of that. Interesting. So I had changed that. Yeah, so that's more like what we're looking for, but then it's doing the thing. I dropped it down to a Gaussian curve. Not let us invert anything. Did I have something plugged in where it shouldn't? This, like, all of the points should be flat on the. Do this. All of the points should be flat on the surface except for. And that too. I'll have to look at the file that Rachel has is working as intended. I will, if I can't figure that out. The logic is the same in that once you start to offset these points, a surface grid, which will create a surface from a grid of points. And that surface is going to ask you for your points. Give it. And the number of points in the U direction. So we can come back very beginning and take our U count. The surface grid, surface from points. And I will put the version of the file that is working on Canvas by the end of the day tomorrow. So we've got our U points all the way back here. It's not working. If we look at our runtime errors, it will tell us that the U count is not valid for this amount of points. And that is because we have one more point on our surface than we have from the base. So all we need to do is addition component, bring our U value into the addition, and I'm just going to use a panel and add 1. So if we add 1 to it, we'll get the proper number, and the surface grid will then be created. If we go through and start turning off all of our extra stuff that's floating around, I'm going to hide the surface again. I used the U value slider that we had in the beginning. So the surface grid is asking you for the set of points that define your new surface, as well as the number of points in the U direction on the surface. It knows which way to build the surface from. And because of the way that the subdivide works, we're left with 1 fewer points than our surface actually has. So I just added 1 to the value that we have and used that as the surface value. The A is plugged into the U count from the subdivide surface. And as you start to play with your graph mapper, that did something closer to what we were expecting it to do. It does all sorts of strange things when you least expect it, but it does start to create a surface. So we've got that. Next thing we're going to look at is creating subsurfaces in a surface instead of just a set of points. So just really quickly, I'm going to same plane. Going to bring it back into Grasshopper as a new surface. And we're just going to run through very quickly how we can break it down into basic sets of subsurfaces. So if we just say plain old divide domain, it's going to divide a two-dimensional domain into equal segments. It's worth pointing out we do have a two-dimensional domain in the surface. We have an X component and a Y component that overlap to create the surface. So we can plug this guy into our domain, our base domain. And right now, we're not going to see anything too crazy. The divide does not actually create anything except a set of segments. But I'm going to use a set of number sliders. Again, I'm going to change them to maximum of 15 and integers. And then I'm going to plug those into the U and the V components. Week 1, 16 or 15 and the other maybe 8. So this is going to give us a set of subsets or subdomains for U and V. You can see this first one is U. It's at one of the corners. It's U is 0 and V is 0, 2, 2.5, and 2.3. And then they continue on. So these are each defining a set of rectangles within the, or smaller two-dimensional domain rather, within the larger two-dimensional domain. Because just like if we had a set of values, we have a set of values in the y or the z direction, and a set of values in the y direction here. So we can always break that domain down just like it were a regular domain of values. Then we'll use a subsurface. Technically, it's an isotrim. So the isotrim is the subsurface, and it's going to extract isoparametric subsets of a surface. So remember that an isocurve is a curve that runs along a surface, right? So the same thing is happening here. We have a base surface, and we have a set of domains that are subsets of that base surface. And it will then create a set of subsurfaces along those domains within the. And if we were to bake this, each of these grid marks would come out as a separate surface in Rhino. So now what if we want to do something more interesting with that? All right, we can do the same thing we've been doing with the graph mapper to change the layout or the relationship of these grids and the subsurfaces that we're creating. So I'm going to surface, turn our base surface back on. I'm going to use the same surface, and we're going to start to break the surface down into a set of points or a set of subsurfaces with variable sizes and relations based on a graph mapper component. So the first thing that I'm going to do is I'm going to deconstruct a domain. And I'm going to deconstruct a two-dimensional domain. But I'm going to use the deconstruct domain numbers. So there are two different ones. One is going to deconstruct it into its component parts. The other is going to actually give you a set of 4 numbers to find the domain. So if we plug our surface into the domain, we have a lower limit in the U and an upper limit, and a lower limit in the V direction, and then an upper limit in the V direction. And the lower limit is going to default to 0. And then we're going to go back and we're going to use our graph mappers just like we did before. At the very beginning, we're going to do something very similar to this, where we use a range to break down the number of subdivisions in a graph. And then we're going to multiply them to increase their intensity. And then we're going to reconnect them and use them to create subsurface divisions this time instead of points. So I'm going to copy one out of the group. and I'm going to use a set of ranges. I'm going to do this twice so that we're going to have a different graph mapping in one direction than the other. Because instead of working in points now, we have 2 dimensions that are. I am, however, going to use the same slider value to count on the range of each one so that we don't run into issues with that later. So if we drop our graph mappers, not our graphed trees, in, I'm going to set one to a Bezier curve, and we can just plug it up so it looks like, you know, a 3rd degree polynomial or something. And then I'm going to use a power function for the second graph. Bring it down. That. So I'm going to then plug our ranges in. So, the Bezier curve. The second one. And I just dragged the anchor points so that it looked like that. Yep. And then the second one was the power curve. You can use the same or different ones. Will work as long as graphs are valid graphs. So this time when we do our multiplication, I'm going to use the u values and the v values as our scaling factor. So we'll make this top one our u value, and we will multiply our output here. You can see, again, very small because it's still between 0 and 1. And we'll use our u value as the other part of that multiplication. On the other side, we'll use our maximum v value and our output from the second graph. So what I'm doing here is I'm relating the outputs from these graph mappers to the maximum values in our domain, which is, in this case, our surface that we're trying to subdivide. And we're going to use a now. So it's going to be shift list. And we're just going to offset all of the items in both lists by 1. So if we look at a panel, we have 12 items. First one is at 0. And if we shift that, we now have 12 items, but the last one is 0. And we don't want to have, remember that these are going to end up being our dimensions for our subdivisions. And we don't want a subdivision with a dimension of 0. So what the shift is doing for us is moving that 0 to the end of the list so that it's easier to start to pull off that 0 when we get to creating a domain. So everything happens in parallel. We're going to shift the bottom list too. Then we're going to construct domains. I'm going to use construct domain. And it can be just a one-dimensional domain in this case. I'm going to use our multiplication as the start point and the shifted values as our endpoint for the domain. We visualize that. We see that we have a set of domains, but now that last one isn't valid. It's 38.5 to 0. A little bit weird. This is where that call is going to come in. But first, we're going to go ahead and make our second domain down here. Again, the multiplication is the first point, and the shifted set is the end point. After that, we can go ahead and find the length of our list. It's going to be list length. It'll tell us how long our domain list is, which is 12, which we knew. But this is how we're going to parametrically call the nth element in the list. So we're going to call that 12th element out, right? Because it's a strange domain that goes backwards. So we're going to use our domain. We're going to call the length component out of the domain. And that's going to give us a list of 11 elements without that last strange domain. Call in. We're going to just copy that down and do the exact same thing below. And then we can construct a two-dimensional domain again. So we have two one-dimensional domains. And now we can construct a two-dimensional domain based on those one-dimensional domains. So our top value, our u, is our u, and our bottom value is our v, sorry. And then we can use those two-dimensional domains to create a subsurface, or isotrim, based on a two-dimensional domain within a surface. So if we come back up and we're going to bring our surface all the way from the beginning down into the S on the isotrim. Is isotrim or subsurface, but it comes up as isotrim even though it's displayed as subsurface. And then we're going to use our two-dimensional domain as our basis. Correct. The domain into the D on the subsurface and the very original surface into the base, the S on the subsurface. And some things should have been flattened or grafted. There we go. So what happened there is that it's the same kind of thing. Remember when we were moving points in the grid, right? One of my values wasn't grafted, so I had a one-dimensional list and everything was only happening once. So when I went back and grafted the hull, I had a set of sublists, so everything went through and happened repeatedly. So if you turn off the subsurface or the base surface, you can see a little bit better what's going on. We've used a graph mapper to create a set of subsurfaces that have variable dimensions. Now there are a number of ways that we can start to visualize what's going on here. Did everyone get this? If you're having a diagonal issue, go back and flatten your col on your U component. So you can just, or graft it, I'm sorry, so you can graft it. That solve it? Yep. Is anyone else still having that problem? All right, so there are a couple of ways that we can begin to visualize what's going on here. But I'm going to load our subsurface, and it's going to bring up all of these lines and points that are in the base subsurface. If we start to look at these points with a point list, we can pull the vertices out of the explode. We're going to need a slider set of 5 probably. So you can start to see that each of these vertices, again, that's a lot of numbers all on top of each other. Each of these vertices is repeating around. So, 2, it's going to be 1, 2, or 0, 1, 2, 3. Right, 0, 1, 2, 3 around each one. 0, 1. So that doesn't help too much. But turn off our numbers, and we can start to pull out items from the list of vertices. So what I'm going to do is I'm going to pull out the 0s and the 2s, right? So that's going to be these corners and these corners of every single subsurface based on how it's all arranged. Yep. And there are 2 of them. It's the list item, not the item index. So our index is 0, our list is a set of vertices, and it pulled out all of those 0 elements, or points we can actually see that. So it pulled out all of those 0 elements starting in the corner. And then the other one that we're going to do is pull out the 2s. Now it's pulled out all of the opposite corners, and we can start to create lines between points. We'll connect across like that. So what I would like you all to notice here is that when you look at those lines across the subsurface and you look at our graph mappers, and you see kind of what's going on here. Got a power function till the midpoint, and then you can start to see the Bezier curve across. So there's that little bit of relation that shows you how we're using the graph mappers, or how you can begin to visualize what's going on with the graph mappers. The other thing that we can do is just drop some sort of polygon or a surface or a circle or something into the centers of the subsurfaces so you can start to see those. Circle can go or center. But I'm just going to drop a unit X in. Yeah. So you can start to see we put a circle at the center of every every subsurface. They start to stack up or split apart. That's just one more way to start to visualize what's going on, whether you use or a surface. Circle normal. So in our circle, it's defined by its center, normal, and radius, because I wanted an easy way to rotate it to match the orientation. Questions about that? Okay. Okay. So and it's not going to. I just turned off the free. That is. Go over assignment. But what I'm going to do is really fast while I dig through my mess of a computer. So this assignment is going to be asking you to create a set of modules and I will open anything based on recreating a facade that we're going to give you.